Hey there, we are Team 55. In this video, we are going to show you how we implemented the Reversi autonomous agents that play and compete in the AI planning for Autonomy Reversi. Let's get started with the algorithms we chose.
We tried the minimax algorithm because it can maximize the value of the opponent's move and minimize the value of our agent's move. Though it may not always find the optimal solution, it achieves the expected minimum loss pattern against strong opponents who tend to make perfect decisions. Minimax computation time is relatively low in depth too compared to other algorithms. Moreover, there is no necessary pre-training time for any heuristic functions. In this way, we can always tweak the weight of them and instantly get feedback. Its limitation is effectiveness. Despite alpha-beta pruning being implemented, the depth of the minimax algorithm was limited at the early stage, which means that the agent could only make locally based decisions affecting the overall result. Besides, the non-optimal solution is a nut trade-off. Later, we will introduce our heuristic function and challenges.
We also deploy A-star algorithms. Our implementation of f-value will be the corresponding scores of each state plus the heuristic value. This algorithm is easy to implement and it performs well against naive opponents such as random opponents. However, the main challenge of both minimax and A-star algorithms is how to design an efficient domain-specific heuristic function.
Thank you, Yiling. Lastly, I would like to introduce Monte Carlo tree search, which is our last methodology. The reason why we choose MCTS is because it is suitable for turn-based games like Reversi that do not involve any chance mechanics. For the selection process, we implemented and compared two multi-arm bandit algorithms, Epsilon Greedy and UCB1 strategy. In terms of performance, we found that there is no significant difference between these two strategies when time is limited. However, UCB1 would increase space complexity and reduce the overall number of iterations slightly, so we choose epsilon greedy with epsilon equals to 0.1. With respect to the rewards function, we decided to give more credit to the simulation process that wins the game, and some penalty points to those who lose. There are, however, some limitations to the MCTS. For each iteration, exponential computation is required as well as a large amount of memory space. Due to this, our MCTS can only explore a limited number of nodes in 1 second. Also, the MCTS would ignore many policies that we discussed earlier. For example, it will occupy some cells close to empty corners, which would result in a loss like this.
Generally, we have considered 3 policies. Let's look at 2 of the scenarios. The main objectives in the opening and middle games is to ensure that we are able to move and limit the opponent's move as much as possible. When the mobility is low, it may be exploited by the opponent and force us to make bad moves. By having the mobility policy, we are able to gain more advantage. It can ensure us to not pass the round and hence lose a chance to play, but it is difficult to implement. We can also see from the image, the opponent has been restricted to have no move to play. It has to give up on that 2 rounds. By having the corner policy, we are able to flip the opponent's pieces in between. Taking as many corners as we can helps to prevent the opponent from taking that corner and flip our pieces in between. We also wanted not to occupy any of the positions immediately adjacent to the corners as there are too many opportunities to get caught in the middle by the opponent's pieces.
When we compare the A-star algorithm with greedy best first search algorithm, we discovered that the greedy BFS can perform well at the beginning of the game. Also, the Monte Carlo tree search is highly competitive at the end. Therefore, our final agent is actually a hybrid agent that combines greedy BFS and MCTS, with greedy BFS handling the first half of the game and the MCTS handling the second half. As can be seen from the 2 tables, the hybrid agent performs best out of all the methodology that we considered. However, there are still many aspects that we can improve. For example, design an algorithm that combines MCTS and reinforcement learning to update the Q value based on each move's feedback. In this way, we will not have to manually adjust each feature's weight, and the weights can be guaranteed to be more accurate. Also, we believe that there is a way to introduce more complicated stability, which measures how vulnerable a piece to be flanked in many different ways, not just corners, edges, and diagonals.
In this demo, we started by limiting the mobility of the opponent, and then around the middle of the game, we prioritized the corner positions if there are corners, and edges positions if there are no corners. Finally, we determined the stability of the position. For example, a corner is very stable because it is a piece that cannot be flipped. We added more weights to the positions that cannot be easily flipped and negative weights for positions that can easily be caught in the middle.